Now let's consider another example using Mendel's P's. And in this example, we're going to tweak it ever so slightly. So in a well-known genetics article written in 1923, there was a statistician named Yule who analyzed data resulting from crossing garden peas. And the dominant alleles in the experiment were R, which represents the round shape, and Y, which represents the yellow color. And this resulted in a double dominant RY. And Yule examined 269 four-seed pods resulting from the dihybrid cross and counted the number of round yellow seeds in each pod. So we'll let X equal the number of round yellow seeds in a randomly selected pod. If we think about the values that X can take on, that would be 0, 1, 2, 3, or 4. And Yule observed in his 269 four-seed pods that 16 of them had 0 round yellow seeds, 45 pods had 1 round yellow seed, 100 pods had 2 round yellow seeds, 82 pods had 3 round yellow seeds, and 26 pods had 4 round yellow seeds. So according to Mendelian theory, our random variable x should have a binomial distribution with n equal to 4 and theta equal to 9/16. You might recall that this 9/16 sounds familiar. It's going to sound an awful lot like the 9/16 we had in the last problem, where we were stating that the probability of having a round yellow seed should be 9/16. So our goal now is to test this claim on the data in Yule's paper using the 1% level of significance. To start this problem, our first order of business is to really figure out the specified probabilities for each category. I've got them written in here, but it may not be obvious where they came from. So let's think about where they come from. In particular, let's look at the first category where x is 0. So we're interested in calculating the probability that x is equal to 0. Remember, this is binomial with n equal to 4 and theta equal to 9/16. So that means we're doing 4 choose 0 times 9/16 to the 0 power times 7/16 to the 4th power, because 7/16 would be the probability of failure here. And if we compute that, we'll get the 0.0366. Similarly, if we do the probability that x is equal to 1, this is equal to 4 choose 1 times 9/16 to the 1 power times 7/16 to the 3 power, and we'll get 0.1884. Continuing in that fashion, we can generate the 3 remaining specified probabilities for the categories. So the fundamental difference to start between this example and the previous example is that in the previous example, the probabilities were a little bit easier to calculate. In this example, we have to do a little bit more work using our binomial probability distribution. So next, what we want to do is compute our expected values, and we'll proceed in a similar fashion as the way we did before. Remember, here we have a sample of 269 four-seed pods, so when we're computing the expected values, n is equal to 269. So if we want the expected value that we have 0 round yellow peas in a four-seed pod, we're going to take the 269 and multiply by 0.0366. If we do, we'll get 9.85. So that goes up in this slot up here under the expected value for the category where we have 0 round yellow seed pods. And similarly, if we do 269 times 45, we'll get the value for the category where we have 1 slot. If we do that for all 4 remaining, we get the following expected values: 50.68 for 1, 97.75 for 2, 83.78 for 3, and so on. Again, let's define our hypotheses. In this case, I'm going to be a little bit more general with my null hypothesis and just say that x has a binomial distribution with n equal to 4 and theta equal to 9/16. Parenthetically, I've written down those specified probabilities for each category, but here it's maybe not so necessary to do that, versus the alternative that x does not fit the given binomial distribution. And again, we'll go to compute our test statistic. We'll look at the observed value minus the associated expected value, square it, and divide by the expected value. So I apologize, there is a typo right there. That should be a 9.85, not a 9.86. Doing this for all 5 categories gives us a test statistic of 4.59. And let's say we compute a p-value for this problem. Our degrees of freedom, remember, is 1 less than the number of categories, so that's 4. To compute our p-value, remember, we're looking at the probability that we would observe a test statistic as extreme or more extreme than the one we observed. In other words, we're looking for the probability that chi-square is greater than or equal to 4.59. And we can use our calculator to do this by looking at 1 minus the probability that a chi-square score is between 0 and 4.59. If we do, we get 0.33. So at the 5% level of significance, we're going to have to fail to reject the null hypothesis since our p-value is so much bigger than our alpha value. So there's insufficient evidence to suggest the data do not fit the model. In other words, the data is consistent with a random variable with a binomial distribution with parameters n equal to 4 and theta equal to 9/16.